Hi, today I'm gonna start to talk about the 2 and 3 force member. Sometimes when we are analyzing a member or an object, there are some elements in that object or that only has 2 forces or 3 forces acting on that. Uh, we want to see how we will analyze on that and what we should to approach when we are dealing with such elements. So assume that we have, for example, assume we have an element look like this. Assume we have an element look like this, and there's a point A here and point B here, and there are 2 forces applied on that. So one of them, let's say, is the F1 apply here, and then there's a assuming F2 applying there. So there's the F1 and F2 applying on the A and B. So I want to see if we have a member like that and there's only 2 forces applied on that member, F1 and F2 at point A and point B, how that member can be in equilibrium. So under what condition this member would be in equilibrium, so then we can do our analysis. If you remember, when we are dealing with the 2D problems, there are 3 conditions we should have or we should satisfy to have the members in equilibrium. The sigma fx is 0, so all the force in the x direction should cancel out each other. Sigma fy should be 0, so all the forces in the y direction should cancel each other. And sigma m about any point should be 0. In other words, all the moments about any point in that problem should be 0. So let's look at how it's going to work out for this very simple element that we have here. So it's a single element with 2 points and there are 2 forces apply on that. One thing I want to mention, remember that every time we were dealing with 2D problems, before we start to do anything, in most cases, as I said, it's easier to find the component of all forces in the x and y direction before I start solving it. So assume I'm going to start to write that component here. So for example, for F1, I have an x component, so it's going to be F1 in the x, and there's a y component, so it's a F1 in the y direction. Then for this also, there's a F2 in the x direction, and there's a F2 in the y direction. Now I will write the first equilibrium equation, see what we are going to get. So sigma f x is 0. So if I write sigma f x is 0, it says that f1x, which is the positive direction, minus f2x, because it's the negative direction, should be 0. And in this case, f1x is f2x. So if I write the sigma fx is equal to 0, I'm gonna find out that the x component of these 2 forces, in the magnitude at least, they are similar. So they have the same magnitude. If I write the sigma fy equal to 0, then I'm going to have, again, f1y because it's a positive, and f2y negative is 0. Then the same way I can consider fy1 is equal to f2y. So the magnitude in the y direction should be the same. So if I look at these 2 conditions, it says that the magnitude, the x component of these 2 forces is the same. The y component of, at least the magnitude of the y components and the magnitude of the x component are the same. So if we have 2 vectors that their magnitude in the x direction, say, their magnitude in the y direction is also equal, therefore their magnitude is equal. So just by looking at these 2, they are equal in the x direction, they are equal in the y direction, so they should be equal in magnitude. So in other words, the magnitude of f1 is equal to magnitude of f2, not the vector wise, but in the scalar, just the magnitude of f1 is equal to magnitude of f2 if I write this. And then if I go ahead, so if I write these 2 equations, like I said, okay, if this condition and this condition is satisfied, the sigma fx is okay. So if all the x is f1, if the magnitude of the f1 and f2 in the x direction is equal, so sigma fx is going to be 0. If the magnitude of f1 and f2 in the y direction are equal, those sigma fy is going to be 0. Also, I have to satisfy sigma m is 0, so I need to write the sigma m is 0. And about one point, I have to choose which point I want to calculate the sigma m. Now, if I choose the a, I write the sigma m about point A, then F2 has some moment about point A, and it's going to rotate that object. So it's not going to be 0. If I write the sigma m about A, here, if I go ahead and write the sigma m about A, then F1 is 0, but F2 has the moment about point A. So there is a moment for a point. So it's not going to be 0. The same if I write the sigma m about point B. If I write the sigma m about point B, the F2 passed through the point, so it doesn't have any moment. But F1 doesn't pass through the moment, and it produced the moment. So also, if I write the moment, it's not going to be 0. If I write it about any other point in here, if I calculate the moment about any other point, the moment is not the sigma, the add of all moments is not going to be 0. The sigma m is not going to be 0. In other words, although under this condition it's going to be 0, but under what condition I have, the sigma m is never going to be 0. So how I'm going to make the sigma m 0? Under what condition the sigma m becomes 0? Is that either this one or any other, or the moment about any other point should be 0. Now assume I want to say that sigma m about assume that I want to make sure sigma m about A is 0. Okay. So if I want to make sure sigma m about m is 0, F1 already passed through A. So it doesn't have any moment. To make sure that the F2, the moment of F2 about point 8 is 0, also F2 should pass through the A. So the F2 should pass through A. So this one says that F2, the line of action of F2, should pass through A. That's the only way that I can get sigma m equal A0. So the direction of F2 should be in a way that it passed through A. Now if I want to make sigma m about B equal to 0, so F2 is passed through B, it doesn't have any moment. What about the F1? To make sure that the F1 doesn't have any moment about the B, then F1 should pass through the B. So if I extend the line of action of the F1, it should pass through B. So the F1 should pass through B. So this one says that F2 should pass through A. This one says that F1 should pass through B. So the only way that happened, the only way that I have that happen is that if I have this, I am going to draw it again here. So there's a point A and there's a point B. And I'm going to connect these two together. So the only way that this is going to happen, the only way that the moment is going to be also 0 is that I'm going to have F1 is being like that, and F2, the same thing is going to be like that. In other words, so that's the only way that F1 passed through B and F2 passed through A and F1 passed through B. In other words, if I have if I have a member that only has two forces applying on that, only two forces apply on that, first the magnitude of the forces should be equal. Let's say the F1x and F2x should be 0. It should be equal. The Fy1 should be equal to F2y. So the component in the x direction and the component in the y direction should be equal. In other words, their magnitude is equal. they are in the opposite direction, and they have the same line of action. So they both have the same line of action. Either in this case that you will see that happen. So in other words, they both has this equal magnitude, opposite direction, and have the same line of action. That's the only way that two-member force can be in the equilibrium. In any other cases, it cannot be in equilibrium. And this is very important. Try to remember that, because later on when we start to talk about truss, that is the concept we use to make sure that that's the concept we use to start analyzing the truss member, because because the truss members are two force element, and we use these concepts. So one more time, if we have one element and only two forces apply on that, first two forces should be equal in the magnitude, two forces should be in the opposite direction, and two forces should have the same line of action to be in the equilibrium. If this is not going to be satisfied, that member is not going to be in equilibrium. The other type of equilibrium that we may consider is that we have the member that has three forces apply on that. And I will not go through the detail, but I will tell you under what condition this might be possible. So the first condition is that, for example, assume I have a beam. The first condition is that if I have, assume I have F1, F2, and F3. So the first condition that I may have the element with three forces be in equilibrium is that first all the forces should be parallel, and also they should cancel each other. So they should be parallel. So if I have one forces that is not parallel, for example here, if I have F2 like that, then it's not going to be in the equilibrium, because if it's like that, there's no forces to balance it in the x direction. If I have push it like that, this object start to move. So the first condition that the three element member can be in the equilibrium is that all the forces should be parallel, and they should cancel each other in the magnitude. The other condition that it might happen is a consider the same thing that we have here. For example, I assume I have the F2 is there, but this time I'm going to have the forces like that. The other times that the member with three forces can be in equilibrium is that all the three forces are going to intersect exactly at the common point. So all the three of them intersect right here. That's the other condition, other way that I can. If there are not all three of them intersect at the single point, then it cannot be in the equilibrium. For example, if the F2 instead of being here, be here, then all the three is not going to intersect in the single point. And because of that, because they cannot intersect in the single point, it cannot be in equilibrium. So the three member element, if the three force element, if I have a member with three forces, either all the forces should be parallel or all the forces should be intersecting one single point to be in equilibrium. Otherwise, it cannot be in equilibrium. If I have a member with two forces, again, the magnitude of two forces should be equal. They should be in the opposite direction, and they should share the same line of action. Both of them should have the same line of action. That's the only way that we have the two-member element or three-member elements be the two-force member or three-force member can be in equilibrium.